Hi, I'm Malak, and I'm going to be talking about the Harvard Watch process. So, for the first question, it's asking why is delta S less than zero for the reaction? So, this is our reaction N2 plus 3H2 makes 2NH3. So, we start with 4 moles of gas and we're ending up with 2 moles of ammonia gas. So, because the number of gas molecules decreases, the system becomes more ordered, which in other terms means that the entropy, which is delta S, decreases and therefore it's negative. Because we have fewer gas particles, it means it's lower entropy. So that's why our delta S is less than zero for this reaction. So our delta H for the reaction is negative 92.4. So what that tells us is that the reaction is exothermic, meaning it's releasing heat into the surroundings. When heat flows into the surroundings, it's going to increase its entropy. So delta S surrounding is positive, so greater than zero. Now, if we're going to increase the temperature, the equilibrium constant K is going to decrease. This is because exothermic reactions is like a system giving off heat. So when you add more heat by raising the temperature, the system shifts to counteract that. So it's going to shift towards the reactants. So if we increase the temperature, it also makes the reaction less spontaneous. We know that because of the Gibbs free energy equation. So for our graph, delta G is plotted against temperature. So this is a very rough sketch of a graph. So our delta H is negative 92.4. So it's going to be spontaneous at low temperatures. And then once it reaches delta G zero, which is our equilibrium, as I have drawn there, and the temperature starts to increase and become positive, the reaction is going to be non-spontaneous. So the effect of partial pressure, um, so when we increase the partial pressure of nitrogen and hydrogen, we add more reactants into the system. That's what it means to increase the partial pressure. So according to Le Chatelier's principle, the system is going to shift to the direction that uses up those reactants. So it's going to shift towards making more ammonia. So delta G becomes more negative. So when Q is less than K, the forward reaction is favored. So that's why the delta G becomes more negative. So it's going to drive the formation of more product, which is ammonia. So this question is asking why are the optimized conditions for this reaction high temperatures and high pressures? So in the real world, ammonia is produced at high pressure and moderate to high temperature. So high temperature increases. So pretty much high pressure is important because the reaction results in fewer gas molecules, as we saw when we moved from 4 moles of gas to 2 moles of gas. So it's going to increase the pressure, which shifts the equilibrium towards the side with fewer gas molecules, which is ammonia. So higher temperatures increases molecular collisions, which means it's going to help the reaction happen faster. But it works against spontaneity. So high temperature works against spontaneity. So it's kind of a trade-off. And so that's why a catalyst is important because it's going to speed up the reaction without needing even higher temperatures for it to happen. So this is the graph we were given, and it shows the equation. And we use the Arrhenius equation for this. And so the activation energy is what we're finding, and it's going to tell us how much energy is required to start the reaction pretty much. So the we get a pretty high number for the activation energy, which shows why ammonia synthesis is slow without a catalyst. So again, showing why it's important. This is what I did for the work. to find the activation energy. So again, using the Arrhenius equation for that. So how does a catalyst kind of speed up a reaction? So it's gonna it provides an alternative pathway pretty much with a lower activation energy. So it's going to allow the reaction to produce much faster, even at lower temperatures. So on the plot, if we were to use a catalyst, what you would see would be that the slope becomes less steep because the rate constant K increases even at lower temperatures. So without a catalyst, the temperature would need to be so high that the reaction would be thermodynamically unfavorable. So pretty much again stating that it becomes less sensitive to temperature and faster rate at lower temperature. So the slope is going to become shallower, but it's going to be the same shape. So for finding Q and comparing it to K, this is kind of like a rough sketch of what they provided us with and how you would kind of solve for it. But we pretty much see that Q is greater than K, which we know means that the system shifts left, so in the reverse direction, in order for it to reach equilibrium. So this is kind of another, just a clear image of the way that I solve for Q. Again, seeing that the value they gave us for K is smaller than the Q that we found. So it'll be in the reverse direction. So yeah. So for partial pressure, they told us that we have 50 atmospheres of N2 and 50 atmospheres of H2 and 200 atmospheres of NH3. They also gave us a partial pressure of NH3, which was 196.3. So I made an ice table, put in all the values, so that we can find X. So using 196.3, which is the partial pressure of NH3 that they gave us, I found that X was negative 1.85. So I used that and plugged it into the equilibrium for N2 and H2. And I found both of those values, which is right there on the screen. And that's kind of how you set it up with K. And yeah, that's pretty much it.